Hello everyone, I am Mohammad Masudur Rahman from Institute of Information Technology, University of Dhaka, Bangladesh, and author of the paper entitled Does Correlational Frequency Have a Relationship with Fault-proneness? These are the outlines that I am going to discuss today in this presentation. Background of the study. Fault-proneness. Fault-proneness is an important measure of software maintainability, stating that how likely a piece of code is to contain errors. It is based on the number of faults found in a software system. Code smells. Code smells are potential indicators of poor design and implementation choices by developers while developing and maintaining a software system. These smells are not programming errors or bugs and do not hamper the program's execution, but make software code complex that affect code comprehensibility and maintainability. Therefore, these are the symptoms that affect software fault-proneness in the long run. There exist a lot number of code smells. According to Martin Fowler, father of code smells, there are 22 types of code smells such as long method, complex class, long parameter list, etc. Problem specification. Since there exist a lot number of correlations in the literature, many of those occur frequently and many do not. However, frequency of all the smell types does not have the same impact on the fault-proneness. Therefore, it is necessary to identify the relationship between frequency of each code smell type and fault-proneness and identify the impactful set of smell types. More specifically, it is important to identify which frequent smell types have more impact on software fault-proneness. Motivation of the research. Remembering a long list of code while developing systems is very difficult for developers. Additionally, since it takes a lot of time, it is very difficult for them to eliminate or work with all the smell types at a time. Therefore, minimizing the occurrences of faults by removing important or impacted but frequent code smells is one of the goals of software developers in the systems maintenance space. Thus, the developers will be enlightened with the impactful smell types, and by refactoring these smells on priority basis, the system's maintainability will be improved with respect to the fault-proneness. Also, it helps researchers to innovate refactoring tools for the smell types on priority basis. Existing literature. Several studies investigated that code smells have negative impact on software fault-proneness. Palomba et al. Confirmed that classes affected by code smells have higher fault-proneness than non-smelly classes. Our work is inspired by their findings about the negative impact of software or code smells on fault-proneness, where we particularly show that frequency of different smell types have different impact while considering individual smell types. Right. Research problem. While the previous work show a significant relationship between smells and fault-proneness, impact of individual type of smell frequency on fault-proneness is still unclear. That is, frequency of which core smell types are highly correlated with fault-proneness. To mitigate this research gap, we present an empirical study aimed at investigating whether there exists relationship between frequency of each core smell type and fault-proneness to identify their individual impact on software systems. Right. Basically, the study consists of 4 steps: formulating research goal, data collection, detection of code smells and fault-proneness, and result analysis. Basically, the research answers the following research question, that is, how is frequency of each code smell type related with fault-proneness? This research question investigates that frequency of which code smell types has relationship with fault-proneness by analyzing their frequency of occurrences in the software systems. Code smell types, which have higher correlation with fault-proneness, are considered as highly impactful smells in this study. Data collection. To conduct the empirical study, we have used 11 well-known Java systems from 2 major ecosystems, Apache and Eclipse, as shown in this table. Right. Detection of code smells and fault-proneness. The smell detection tool Decor has been used in this study to detect 13 types of code smells because the tool shows good accuracy and has been widely used in the earlier studies. Detection of fault-proneness. The fault-proneness of a class is measured as the number of bug fixing changes in a class from its previous to current analyzed version. As after fixing a fault, it can be detected from the source code, right? Furthermore, we split fault-proneness based on the classes of each individual type of the 13 code smells to have smell level fault-proneness. For example, fault-proneness of classes having anti-singleton smell type are separated to have of that smelly fault-proneness. In this way, we actually have 13 types of fault-proneness for the 13 code smell types. Our study is based on the frequency of code types and fault-proneness in the systems. Therefore, before analyzing the relationship, we define the following several metrics for this study. Smell frequency, frequency of occurrences of a code type in a system. Total smell frequency, frequency of occurrences of a code type in all the analyzed system. Average smell frequency, that is frequency of occurrences of a code type per system, right? Fault-proneness, number of faults of a class in a system. Specifically, we calculated fault-proneness for a codesmal type as the number of faults of class having the codesmal type in the system, right? Then total fault-proneness, number of faults of classes in all the analyzed system. That is, we calculate total fault-proneness for a codesmal type as the number of faults of classes having the codesmal type in all the analyzed systems. Result analysis. This table shows the overall results of our study as well as the metric values as discussed in the previous slide. The table shows the list of code smell type, total smell frequency, total fault-proneness, average smell frequency, average fault-proneness, and the correlation between smell frequency and fault-proneness. We will discuss these results in the following slides. The research question, that is correlation based impact analysis of codesmal types on fault-proneness. The earlier table, that is table 2, shows the result of the correlation analysis between frequency of each codesmal type and fault-proneness. The findings will be discussed here. First finding, it is noted that we have excluded 4 codesmal types from the analysis because most of the system do not contain any faults for those smelly classes, indicating no relationship exists. Therefore, the table shows not applicable values for those smells, right? So the last 4 code smell types shows not applicable values here. Second finding, we have found an interesting observation that anti-singleton blob class data should be private and long method have a strong correlation, that is high relationship with the fault-proneness, while their average smell frequencies are not so high except for long method. Third finding, medium or moderated correlated smell types, complex class, large class, and long parameter list have high frequency. Lazy class smell type has both medium correlation and frequency. Fourth finding, base class should be abstract, have both small correlation and low frequency. Last and important findings, it is expected that lower frequent smell types have lower fault-proneness because of their lower number of classes in the systems, right? Therefore, for the research question, we focus on the high and moderate correlated smell types, where we can see that their smell frequencies are almost opposite of their relationship strength. That is, high frequent smell types have moderate correlation and moderate frequent smell types have high correlation, right? Conclusion. Our results clearly show that code smells have negative impact on software fault-proneness, and frequency of all the smell types does not have a strong relationship with the fault-proneness. Certain types of smell types such as anti-singleton blob class data should be private and long method have high impact, though their frequencies are not very high. However, it is important to regularly monitor and address the impactful code smells to maintain good software quality and reduce the likelihood of faults. Moreover, the short list of high impactful and frequent smell types helps developer to prioritize code smells to be refactored while performing maintenance activities. In addition, our findings not only help practitioners but also researchers to develop refactoring tools based on the smell impact. As for future research, we will focus on other maintainability aspects such as change-proneness to measure the impact of the individual code smell types. These are the references used in this presentation. Thank you, everyone.